Hello there, hope you're keeping well. Welcome to the wonderful world of radio frequency and electronics engineering. On the bench today we've got two microwave RF power sensors here with a frequency range up to 26.5 gigahertz that we're going to be testing. And these sensors came to me via a friend of ours that we meet quite regularly, and who purchased these microwave sensors but didn't have a power meter in order to test it. And it turned out that I didn't have this meter either. I have some earlier ones than this, the old style ones, but my friend suggested that he had one, so he's loaned me this meter to help our other friend test these. So between us we've sort of got it together now where we can do a proper test for this this friend of ours who's got these two sensors. So the reason why he's given these to us is because he didn't obviously have the meter or the precision adapters that go at the end, because these are obviously precision connectors and we've got the precision adapters. So today what we're going to be doing, we're going to be using these adapters in order to connect to these, and we're going to use this meter, but we're also going to check this meter for accuracy as well using the Marconi microwave radio test set that I have here. Which we're going to look at in a moment. But basically these sensors have these weird precision connectors at the end, like a lot of them do, and I have a series of adapters here which adapt to different genders and one thing and another, and we use these quite commonly, and I've adapters for Roden Schwartz, HP Agilent or Keysight, and Marconi as well, Marconi instruments. So we've got a precision adapter in the end there on this one. We're going to be testing this. Now all these sensors come with some data on them as well, which gives us things like calibration factor, or cal factor as it's known as, linearity data, and then cal factor information for each frequency as well, so in the table here. So we can enter that into the meter as well, which takes some time to do. Now there are different types of sensors which are available. There are thermocouple sensors, and there are also diode detector sensors as well, so there are different types. Now the meter recognises the different types because it reads the sensor when it's connected in, and we can use the meter to calibrate the sensor by using the cal feature which is on the meter, which is these cal buttons here, and we have the type N output here which gives 0 dBm or equivalent to 1 milliwatts at around 50 megahertz is the cal signal to these sensors. So that's initially how we'll know that these sensors work. So obviously that's the first thing we'll do after we've entered all the cal data in, set the meter up correctly so that the sensor will calibrate properly. Then what we'll do using the Marconi microwave radio test set, we'll check the 50 meg reference coming out of here for accuracy as well, out this meter, and we'll also do some sweep power measurements using this particular sensor as well, across its entire frequency to 26.5 gigahertz. So let's have a look at the Marconi equipment that we're going to use to test both the meter and this as well for accuracy. Okay, so just to explain what's going on here, we've got the Marconi microwave test set up. After 1,000 years, when you've entered all the calibration factor, linearity factor, all the frequency table, you know, as per the sensor calibration data which accompanies the sensor, then essentially you set the sensor up in the Marconi microwave test set to essentially measure correctly, because without that linearity data, cal factor and all the frequency tables representing all the response, then the sensor wouldn't read properly. So now we're ready to begin a calibration sequence. So what we've done, we've connected the sensor now to the power reference port, which is what it's plugged into now, and then we're ready to do a calibration. So we've got the screen of this microwave test set. This particular microwave test set we're going to use for two things. we're going to use the microwave test set with the power sensor here to verify the HP meter that we're testing has a 0 dBm output from its calibrated reference port. Otherwise, if the output of the meter isn't correct, then its sensor won't be calibrated correctly against it, so all its measurements will be out. So that's test number 1 we're going to be able to do using this sensor. But test number 2 is this particular microwave test set has a frequency range up to 46 gigahertz. So we're going to be using this as a frequency sweep at 0 dBm, and we're going to check the sensors on the HP meter read correctly up to 26.5 gigahertz, which is the sensor's usable frequency range, these sensors. So we're going to be using that test set for that particular test number 2. So what we've got, the screen here is not particularly good on these microwave test sets from Marconi. It's like an LCD screen. They've always been quite dimly lit, these backlights on them. They're not particularly great. So we've got a breakout screen here, which is this particular screen. So if I go into sensor cal now, obviously we've got the linearity, cal factor data in there. We've put all that jazz in, and now we're ready to do a continue. So it's now going to 0 the sensor, and then we're going to continue with that. So it'll just take a few moments for it to whiz through that, and then we can begin our measurement then on the HP meter. So what I'm looking for essentially after this is 0 dBm reference on the Marconi test set. Should read 0 dBm on this particular sensor. So I'll check that first, and then we'll move it over to the HP Agilent meter and then test that, and then we can start testing the sensor then. So there we are, it's all done. It says there sensor calibrated, so we've done that particular thing already, so that's great. So now when I put the sensor power on, we should be getting 0 dBm, and that's what we're getting, 0 dBm. So this microwave test set is actually fully calibrated. It's not something that's out of cal, it's all in cal. Is this, it's been calibrated, so we know that's going to be a good reference starting point. Okay, so we'll disconnect that now, and so I'm just going to unplug the power sensor there on the front of this Marconi now that we've verified that. So we'll disconnect that. Never turn the sensor, always turn on all these sensors, always turn the outer collar of the connector, never turn the sensor round. I see people doing that, and it can cause damage to the sensor. So here we are. We'll come down to the sensor now in here, and we'll just reposition the camera so we can see the screen, and we'll do a measurement on this. Okay, so what we're going to do now is we're going to use the Marconi microwave sensor that we've already calibrated now on the calibrated MTS, and we're going to connect it to the Type N reference power port on the HP meter so we can test the accuracy of that meter. So that's what we're going to do now, and what we do is we support the body of the sensor, and we turn the collar to the Type N. Never rotate the sensor because it causes damage. They're gold plated contacts in the Type N, which must be kept damage free and clean, so that's why you never turn the body, and it causes damage to them. So what we'll do now, we'll turn on the reference power excuse me, on the meter by pressing shift and this button here. And now basically what we've got output power from that port now entering this sensor for measurement. So what we can do now is we can go over to our Marconi power meter measurement now in the microwave test set. So considering this, according to the label on the front of the meter, this was calibrated in 1999, this HP meter. So it's not bad, you know, considering it's 25 years since it last had a cal, and it's plus 0.052 dBm. And so we can adjust that probably and get that bang on 0 dBm, so it matches the Marconi as well. So we could do that for my friend's meter. But before we do that, I just want to see how we are with the HP sensor that we've got for testing. So I'll do shift and turn the power reference off so we can connect our sensor that we need to test, with two of them obviously to test. So we'll do the first one. Now the cal factor on this particular one, according to the table, is 100% on the cal factor there. So basically this data, I've already entered it in, and we can see there, look, the cal factor is 100%. And then basically in the meter, which I've already done, you can enter in each one of these, the cal factor for different frequencies, all the way down to 26.5 gigahertz. So after 1,000 years of entering all that in manually into the meter, then you actually get to a stage where you can then be ready to connect it and calibrate it. So that's essentially where we're at now. So that's the only lengthy process if you want highly accurate measurements, obviously. So this time when we do a cal, it'll ask us for the cal factor, which is 100% as per what's on the sensor, and then we just hit enter, and now it's going to cal it. Now as part of that process, it'll range it obviously, and then it'll deliver the measurement there. Now if I do shift and reference again, then it should read 0 dBm, so that's correct. So now what we can do is we can do swept frequency measurements on this right up to 26.5 gigahertz, and see what the power meter is reading there at 0 dBm. So we're going to use the microwave test set again, and this time we're going to set up a measurement here where we are going to, if you like, set up a swept frequency measurement. So we're going to go to set the start frequency, and because this particular probe has a frequency range of, if I just have a look very carefully at the label, obviously we'll say 50 megahertz. We'll put that in then, so 50 megahertz, and then we'll set a stop frequency of let's see now, 26.5. It's already in, so I don't need to mess about with that. Right, 26.5 gigahertz. We'll set the output power as well to 0 dBm, and the number of points 401. We'll leave it at that for the time being. Sweep time we'll leave, and I think under select source mode, yeah, we've got start stop frequency there, so that's all correct as it should be. Right, so now I need to just start the measurement. So I will connect this now up to the RF output lead now on the Marconi test set, and then we'll come back. Okay, so we are now generating an RF frequency sweeping right the way up to 26.5 gigahertz, and it's doing a slow sweep because I've reduced the sweep time. But as we can see, the accuracy at the meter is very good indeed there, and proves the sensor's working. Obviously, if I change the output power, so I'll just change the variable Let's have a look now, get it right the way down here to a lower level just for demonstration purposes. And right, so let's have a look here. So that would be, as it reads on the Marconi, minus 10 dBm, right up to 26.5 gigahertz. So as you can see there, it's quite accurate. You know, it's just, you know, 0.1, 0.2 of a dB, possibly 0.3 at the most of a dB off. In this case, obviously, because the meter's reading slightly, well, its output slightly out on the reference, but it proves the sensor's reading fine without problem. Obviously, if I put the power back to 0 dBm, then we jump back, and obviously if I turn the RF power off, then we revert back to the noise floor of a sensor, then re-establish the RF power, and then we're back again. So, you know, it's reading accurately, is that sensor, there's no problem there. Can't see there being an issue with that. So at least that proves that particular sensor works okay. So I think it's just a case now of testing this sensor the same, and fingers crossed it'll be okay for him. So right, onwards and upwards. We'll put the next sensor on. Okay, so we'll disconnect this and then connect the other sensor on, which is obviously not being used because it's still got this protective Captain tape over it, so protecting it, so we'll have to peel all this off. Just put that to one side a second, and same with this. This looks like a new sensor that's not being used. Connect this up, just see whether we can get it to connect up. Just have a look at the linearity factor on this. That's 100% as well, calibration factor rather. And then we've more or less, let's just check the frequency characteristics of this on the table versus the other. I doubt they'll be the same, but you never know. No, they're different obviously. I thought as much. So I'll have to enter in all this data now into the meter, which will take me quite some time to go through all that again, and then we'll come back and carry out the tests on this. Yeah, this sensor, it won't zero for some reason. I've just tried zeroing it because it came up on the display 0, but when you try zeroing it, it won't zero for some reason. Don't know why. Might be worth us taking it apart and having a look, just see if it's something simple, like the wiring loom for the plug there, perhaps. Which it says cannot zero though, which is strange. I wonder if it'll calibration factor's 100% again on that one. So let's see whether it'll cal 0 dBm. Just reading 0 dBm. Function cal. Yeah, enter. Ranging. Please 0, which if you try and zero it, it won't zero. But it is reading, it appears to be reading the RF level correct anyway, but it won't zero. It's trying to, but then it says it cannot zero it. But yeah, if I do function power reference on there, it does read 0 dBm more or less. So it's just the zeroing function won't work on it for some reason. I don't know why that is. Unless there's something wrong with the connector is turning. When I do that socket is moving about, and it is affecting the measurement as well, as you can see there on the meter as I'm rotating that. It's the socket that's rotating. So I might have to take that apart and have a look at it, but it won't zero, that's for certain. I wonder if it'll zero if I move it. Yeah, cannot zero. It's definitely having an effect. Is moving that. Try again, zero it. So there does seem to be a problem with this sensor, although it's reading RF okay, that particular case on the reference output, so there is something wrong with this. We're going to have to look at that. Right, I'll connect it up to the Marconi now and just see whether we can get a reading of the RF power. I'll just do a preset. That's it, preset it. That way then at least we can get back to some kind of RF level reading. It says please zero though, but I don't know if it will work until it's zeroed. So I'm just connecting it to the Marconi radio test set on the output, and let's see whether it reads RF. If we can get it to read RF, that'd be nice. So I'll turn the RF power on, and it does. So that's a swept frequency again up to 26.5 gigahertz at 0 dBm, and again you can see there the accuracy of it, but it just won't zero. So that's the only problem with that sensor. So I'll just have to switch the RF off and then let's have a look and see what we can do to get it going. It looked new to me, did this sensor, because it had this Captain tape protecting the RF side of things, but that is moving. As you can see, the socket's loose. So yeah, interesting. It doesn't look like as if it's anybody's been into it. Adjuvant calibration void if removed, etc. So there's nothing there, but that's definitely rotating round is the body of that. I wonder if a wire's come off inside maybe, and I'll have to open it up somehow and see whether we can get into it and just feel for some screws. I assume the screws are under this label somewhere in order to get into it, unless it's under these sides. I can feel some indentations, so I'll have to have a look to see whether I can open it up, and then we can have a look at this this connector, seeing as it's turning round there and it shouldn't turn, and it's loosey goosey there, so we'll have to do something. Back soon. Well, I found out after a bit of messing about that they just unclip these plastic case parts, and then we've got this, so it just drops off, and then we can get into it and using these little screws. But that's that was definitely turning round. That, let me just connect the lead back up. Yeah, definitely loose. So hopefully it's something simple. Be a shame if it were broken so to speak. But let's have a look. Right, so in my this looks weird. It's like some kind of Torx thing with the look of it in the end there. So let's see what we can find in the screwdrivers. Okay, we've found something that fits, so that's good fortune. I'll just undo that. Seems to have held captive these screws. I'll drop them in there. Those little plastic things. Don't want to lose them, because once they drop on the floor, never find them again. They will definitely disappear under these, so always be careful. Make sure we save them. And let's see what we find in here. Very carefully open it up. And just being extra careful. There's some more there on that side. I can't see though how it's held together. Its body, it just seems, must be the these there. I'll take those off because I don't want to yank this out, because it seems to be held captive, does that. So let's just remove these as well, and these screws that are there. May as well take those off as well. And hopefully I'll leave one screw in, and I'll just remove this top lid. So I don't want to damage any RF substrate or anything like that. So I'll leave one screw in on the bottom plate and see whether this lifts up. And it does look like it does lift. So let me just see if I can gently pry it. Not causing any damage, of course, because these things are so easy to damage. And can't pry that, but I can pry this side here. So it seems to be opening up. I'll undo that last screw then. See if it's held in place. Seems to have tightened it up. Let's very carefully just remove this top cover. So it was just as well that I didn't try and force it, because of those little gold wires. So what I'll actually do is put a screw back in there, just to prevent the precision RF connector from being pulled away. And I'm wondering if with this dropping off it's shorting something and preventing the zero in action. So let's just have a zoom in on that and see what we can see. And so let's just zoom in and have a look at that sensor a little bit more. So we've got the wires coming out the sensor, because obviously it's thermocouple or diode, it'll be the collar of this connector there, and they then connect down onto there. And then of course we've got the this collar here is loose, that's shaking about inside. So is it touching pins and then not being able to zero? I don't know. Just going to have another further look at it under the magnifier that I've got here, to see if I can see anything with these wires or anything, if there's any wires damaged or coming off. Can't see anything, but I'll just lift this up a second. Ah, look. Looks like we've got something missing here. We've got a bit of a condom thing there, look, connecting there, and it looks like there's a wire off then. So let's just move that up there, and I can see a wire. So we have a wire off, which is just under there. You can just see it there, look. Bit tricky to see, but I can see the culprit. So that needs connecting back up, doesn't it? This wire. Let's see there, look. So we'll connect that back up to there, I think. That's obviously come off. So that might explain why it won't zero then. So yeah, interesting. Okay, so let's see what we can get done. Yeah, so I've just nipped up this nut there using these pair of long nose pliers and giving it a bit of a twist. I mean, you don't want to nip it up like Arnold Schwarzenegger would with your vein popping out your neck, but as long as it's you know, tight up, because there are some little lugs, you can probably just see them there. I had to rotate this connector around so that that little lug keyhole went in the body so it won't rotate, and then just nipped up this nut. So I put a new condom on. We've got a new Johnny on there, so the old one was all broken up and haggard, so I put some of those sleeves on. So I think it's just a case now of cutting this wire back and then tinning it. So we'll knock the soldering iron on in a second, but I've just got I've got my magnifying glass set up for this wire, because you know, when I was about 20 years old I could see a flea on a fly's backside, but now I can't see anything unless I've got my magnifier. And it's amazing as you get older how your eyes get worse. And I used to be able to do all this work years ago without any magnifiers, and I could see things. And I remember older people in the workshop where I worked that were coming to me saying, can you see this, can you see that, can you see this serial number, can you see that circuit diagram, can you see this wire? And I used to say, well, why can't you see it? And they used to say, well, I just can't, you know. And some of my glasses as well, and I used to think, well, there's something strange there. And little did I realise that about 30 years later I'd be the same. And I'm asking younger people myself now in my job, you know, can you see this? Because I can't. So, right, so we just need to tin that and then get it back on that little pin down there, hopefully. And then fingers crossed, you know, hopefully it'll work. Back in a moment. Okay, I managed to get it soldered, and I'll just push my condom on. So there we go, look, that'll do, and that should do it. Put it back together then, I think, and just hope for the best. Now, I did notice that that wire did actually go via that transistor, but we'll see how it goes when it's all pushed back in, because I don't want to try and force things, you know, unnecessarily. But I think it just needs to push in. Possibly, I think it might go round there. This is a bit tight, you know, how it all goes together. That looks okay. That's there, that's there. Yeah. So I'll put the screws back in, just on the back there, hopefully. Then that should keep it going a little bit until we can do a test. Zeroing it as it is. Probably put the case on so that it's, you know, it zeros without the noise, because obviously having the case open allows a noise to come in. So I just put the cover on and then connect it up to the meter, and hopefully it'll zero. Well, it's measuring RF okay, but who knows. Oh, now we can't get this screw in now, can we? Oh, there we are, look, we can get that screw in. Okay, so, and all looks good. I mean, obviously, if you were to undo these two screws there, and there's no screws holding this precision connector on, and you were to pull that connector this way, it will break these gold wires off, these very delicate gold wires, and that's what you have to be really careful of, because when they break, you've had it. And you can be guaranteed that if they were to break, they wouldn't break in this area, they break inside there in the collar. That'd be the wires that get pulled out, and that's it, you've had it. But basically it just goes through. You can just see there, look, the gold wires they're pressed down with this plastic like plunger onto the IC, this IC there, which you can see, and that's how that works. But yeah, you've got to be really careful, because I guarantee to you, when these gold wires, these fine gold wires on the Marconi sensors, they're even thinner than this. They're like human hairs. They're probably half as thin as these, and so delicate. And the thing is, because they're solid gold wires as well, you can't solder onto them, because the melting point of a soldering iron is higher than the gold melting temperature, and they just melt off when you try and solder to them, if you try and extend the wires, if you get a breakage or anything like that, because they're obviously bonded. But yeah, they go through this little spacer, and then they actually go onto the IC. There's two pads on the IC there, and you can just see the gold wire just gets pressed down with this plastic spacer onto this IC, so it reads it directly. So we've just got to be careful about removing all the screws. Leave one screw in at least, and that way then at least you can't sort of pull the thing apart. And because if you pull it apart this way, obviously it'll damage it, so that's something to be worthy of. Similarly, if you had, say, the case on the top here, and you had these two screws in, but you then withdrew these two, if you were to then lift this with this connector, because obviously that would be connected to the top bit, up and away, this PCB is attached, bolted down to this cover, whereas the connector and this will be connected to the other cover. So as you withdraw this socket with it and pull it away, then these gold leads will snap off, because this PCB is fastened to this shell, and the connector in essence would be fastened to you know, this top bit. So you know, if you had the screws in this top connector there, and you took the screws out there and there, these two, and same, you had the screws in there and you took the screws out there and there, when you withdraw this, it'll pull that connector away and pull the gold leads off, because the PCB is fastened to this shell and the connector will be fastened to this. So it's always better, I think, if you are removing these covers, to leave the screws in on the same side, and then just remove the other side, so you're not risking that where your PCB and your connector on two different shells and they get pulled apart, causing damage. Obviously it's something to watch out for that if ever you have a venture into them yourself. But right, we'll just bob this shell on then. I'll just push it on for the time being. I don't think it's handed, although I'll keep it the same. I think it goes that way, because I found these these holes there sort of line up with those, so I'll keep it the same. And obviously, because I've put the screws in now, it won't go back together, will it? So I'm gonna have to slacken these two screws off here just a bit, because it's quite tight tolerance, obviously. So let's have a look. There we go. Right, I don't think it clips together in a particular way, just literally gets pressed in, and then when these screws are tightened up, then it clamps it, obviously with the other screws in as well at the top there. But it's just to see if it works. Okay, so the moment of truth has arrived. So it says there's no sensor at the moment. So if we get our connector, wherever that's disappeared off to, got it, here we are. Right, so we've got that and that. Okay, so we'll just connect it up. Right, let's just feel for it. Oh, there we are, look, that's it there, look. Okay, right, will it zero? Let's just try a 0. That's looking more promising already. That's it ranging. Okay, we'll connect it up to here to calibrate. Or I'll have to get my precision adapter, wherever the hell that's gone. Here we are. And hopefully. Right, let's have a look. Okay, so we'll connect it up to there. Okay. Please 0. Okay, we'll 0 then. Probably detected some noise or something. There we are. Right. Now cal. So shift cal. 100% cal factor. Now we're calibrating it. So if we do shift reference 0 dBm. So that's working. Wonderful. Right, what I'll do is I'll put it all back together with a shell thing on all the screws, and then we'll connect it to the Marconi microwave test set on the sweep measurement from 50 megahertz to 26.5 gigahertz, and just double check that it's reading correctly. Back soon. Okay, so just connected the probe up now. Just turn the RF power on, and what we'll do, we'll just have a look there. We're getting 0 dBm, which is good. I'll type in about set output power on this thing to say what is it, minus 10 dBm or something. 10 dBm. So that's the minus 10 dBm setting. So as you can see, it's quite accurate. So that's at 26.5 gigahertz as well. Spot frequency and the frequency sweep. So it's reading correctly as it should be. So that just shows that that's all fully functional, and just like the other one, should be okay now to be returned back to the user. Right, so we've got the Marconi sensor plugged in on this meter. We whip the lid off so we can calibrate it against the Marconi calibrated test instrument. Now just under here there's a potentiometer, and it says, if I zoom in you might be able to see it, it says reference level there, and it's this potentiometer there. So we've obviously got the RF output here coming away, and that obviously makes its way down the side here to the front connector there. So that's what we're going to be adjusting using our trimmer tool, and we're going to switch the RF output on by going across to the front here, and I think at the moment it says no sensor or something. So we switch on the cal output by doing the shift and then this key here, and that then switches on the calibrated output. So if we then go to the power meter reading on here on the microwave test set, and then what we're going to try and do now is adjust that potentiometer that we've just seen for close enough to 0 dBm as we can. And obviously you don't do this when the instrument's cold, you know. I mean, my microwave test set's been on a few hours, and so is this power meter now. So you obviously do these measurements when things are warmed up. So I'm just starting to adjust the potentiometer now one way. That's it, we're getting it coming down now where we need to be, and then ultimately we can be, well, let's bang on, I think. I hope anyway. Oh, hang on, going back the other way now, gone a bit too far. Let's get it to 0 dBm spot on as we can. So I think we're okay there. Let's just have a look at measurement functions, and default, duty cycle imaging, max hold, counter resolution, return to measure. Right, so I'm happy there. I'll just leave it to settle a second and just have a look at averaging a second. Return to measure, dB relative, general setup, sensor characterization. No, I'm happy with that. I'm happy with that. So I'm just going to see, we can see here, averaging. I'm okay with that. Right, we'll just begin another twiddle just to see whether we can stabilise it a bit more, because it's crept up a bit. Alright, we'll take it down a bit more, because we need settling time, obviously, for the meter to get back to 0 dBm. Just try and settle it out. See, it gets to 0 dBm and then it settles and then starts to adjust itself again. Right, so we'll just twiddle it back the other way again a little bit more. So I think it's starting to settle down now. See what it does now. You have to give things time as well. You get little adjustments and then come back to it and then do another little adjustment, and things change just ever so gradually. Then you slip it back into another adjustment. Just very carefully adjusting it. And as close to 0 dBm as we can get it with that sort of temperature stability, because temperature characteristics are changing all the time unless you've got stable temperature, and it's warming up gradually, and you know it's sort of got up to temperature, but it just drifts a bit because of this potentiometer in a variable resistor. But we are so close now to achieving perfection. And then you just leave it to settle in between each measurement. So let's see where that gets us. 0.002. Takes time, you know. Just trying to settle it. Settle it down. It's not something you can do quickly, this measurement. It'll get there eventually. And then wait for it to creep again. I think that's the longest it stayed at 0 dBm since we started the measurement there. Just creeped again, just creep it back. Just starting to go back that other way again. So I think that's about as accurate as we're going to get it. I don't think it's possible to get any accuracy more than that. I mean, I'm just literally breathing on that variable resistor, and already it's making a marked difference. I've got to touch it, you see, with the trimming tool for it to be enough to knock it off, you know. Right. Okay, so I think I'll leave it at that then. Right, so we've removed the trimming tool now, we've let it settle. It's been like that now for several minutes at 0 dBm. So it's just settling time, that's all. When you put potentiometer on, any slight adjustment or slight tapping of that, just putting pressure on it with the trimming tools enough to get it to start moving. But as you can see there, we're fairly stable now at 0 dBm. So I think we'll put the lid back on, and that's the meter calibrated. Okay, so I think that's more or less the end now. I think we've done pretty well. We've calibrated the reference output on the meter. After 25 years it's been set up again, so my other friend will get this back now, all calibrated. So if he gets sensors for his meter, if he hasn't got them, at least he knows that it'll be calibrated. And the other friend of ours now will get one repaired sensor back, obviously, which wouldn't zero, and then the other sensor worked fine without an issue, and we've verified both sensors on this meter as well as using the Marconi microwave test set on a sweep test up to 26.5 gigahertz. So obviously the sensors are good, so I'm sure our other friend will be very pleased about that. So I think we're quite lucky really with the sensor that won't zero, and we're also very lucky that the sensor in the collars here on these precision connectors wasn't burned out, because it's so common on these where people were not familiar with these power sensors. They see the word power meter and they assume that they can input high levels of RF into these directly from a transceiver that may be doing anywhere from 5 watts all the way up to a couple hundred watts. So it's quite often you get these sensors cheap at places that like eBay and other things, sometimes where it says for parts not working, and it's often the sensor in this neck that's burned out. When that happens, I'm afraid the sensor's written off, because these are thousands and many thousands of pounds to buy each of these sensors. So naturally when that happens, then that's it, it's bin fodder. So yeah, I think that's about it really. I don't think there's much else we can say about this meter. Obviously quite a nice little functional meter, and quite nice sensors. So I've certainly enjoyed making the video. It's been quite good being able to verify and do a repair as well, and find the fault and resolder that wire back on, and make sure that all the alignment of the meter's been done correctly. And we've verified all the specification and performance, but it's always worth remembering with these though, always to treat the sensors with respect, and because they're so easy to damage and blow up, so always look after them if you have any yourself. So with that, bid you farewell, and we'll see you in the next video. Bye for now, and don't forget, if you want to leave comments below, by all means please do. Catch you again. Bye bye.